This is Team 4's group project for Fall 2016 Intro to Particle Technology. Cyclones are used for solid particle separation from wet or dry fluids. Cyclones are effective through use of centrifugal forces and pressure drops. The pressure drop causes the vortex to move downward to escape from the outlet. As the vortex descends, it pushes the particles downward and into the hopper, and clean air escapes through the outlet with minimal fine particles. Cyclone efficiency is best for particles ranging from 10 microns to 1 millimeter. Particles smaller than 10 microns will not be effectively separated from the fluid. Density also plays an important role, as less dense particles will cause an issue with separation. For our design, we chose a reverse flow cyclone. This means that the inlet flows tangentially to the body, as shown in the simulation. Cyclone dimensions are crucial to ensure proper separation. It is clear that the larger particles separate easier, and the fine particles tend to stay suspended in the flowing vortex. To achieve proper separation, the outlet must drop into the body of the cyclone, below the inlet and above the conical section, to allow the vortex to flow properly. Other important design factors are the diameters of the body, the inlet, and the outlet. The body needs to be longer with respect to the diameter. The inlet and outlet need to be small, but they vary with respect to the airflow. Higher airflow allows for larger inlet and outlets, and vice versa. Cyclones are used widely across a variety of industries, and they are used both wet and dry. This is a hydrocyclone applied in a large-scale industrial setting. It receives a slurry of mostly water and coal, and it continuously separates the coal for use elsewhere. Cyclones such as this have low maintenance costs due to simple designs and having no moving parts. They are also able to process high volumes of material continuously. There are some important safety concerns to take into consideration with industrial cyclones. Various risks are associated with cyclones such as dust and static buildup. A buildup of fine dust particles can cause dangerous explosions if an ignition or heat source is present. Fine particles also can cause static buildup, which can ignite dust explosions or flammable materials. Cyclones commonly use flammable and corrosive materials, and it can make the output hazardous or corrode the cyclone faster. Safety precautions need to be addressed to mitigate hazards. For example, the issue of fine dust particles in the air. Personal protective equipment like respirators can be used. Suppressants are also commonly used before or within a cyclone to decrease the chances of ignition or explosion. Most of these risks are associated with industry. Our main safety concern was with inhaling the escaping particles. Our design utilizes a 5-gallon bucket for the body and a 2.5-gallon bucket for the hopper below. A hole was cut in the base of the 5-gallon bucket to allow the particles to drop into the hopper. We also installed a funnel in the base around the hole to guide the particles down easily. We used a shop vac we had available for our pump because the flow rate was high enough to ensure separation. We cut inlet and outlet holes into the bucket using a hole saw for our flow streams. Finally, all of our cracks were sealed with caulk, and we applied duct tape to give extra stability and seal any missed areas. This is a picture after we finished construction and our cyclone was disassembled before our testing. As you can see, extra duct tape was added along the interior to give a smooth surface for the particles being separated. Next is an assembled photo of all of our pieces. To ensure an airtight seal, we applied duct tape around where the buckets connected. We went to the store and got various materials to test. We decided on sugar, salt, and flour because they have varying particle sizes and varying densities. To further analyze our cyclone's efficiency in regards to particle size, we separated our materials with sieves before testing. Once the data was collected, we compared our efficiencies of the different sizes. Following is a sample of our testing. After conducting experiments and collecting data, it was clear that the Cyclone worked best to separate the sugar and the salt. Further analysis shows that the smaller particles, despite what material they were consistently less efficient. We faced some challenges along the way with the design of our Cyclone. The most difficult aspect of the design was ensuring an airtight seal at all points. Another key aspect was connecting the hopper so that it could be detached. As shown, the hopper had to be reattached for each test using duct tape. This did not affect the results due to the duct tape being airtight, but was the main design flaw in terms of ease of use. Another flaw not discussed was that we used an old shop vac with some wear and tear. It did not have a perfect seal for the air flowing in. However, the flow rate was so high that it worked well nonetheless. Overall, Cyclone separation is effective for separating small particles from wet and dry fluids. Our results show decreasing efficiency with decreasing particle size. This coincides with the range of particles being 10 microns to 1 millimeter. However, each particle species should be evaluated individually because higher density material separates much more efficiently than low density. This project gives great insight into why cyclones are used so commonly in industry. They are cheap, efficient, simple to run, and widely applicable.